Hello everyone, in this video we'll be discussing proofs, and the first thing I want to talk about are proving techniques, and there are actually 4 we'll be discussing in this video. There's actually technically more, but these are actually pretty, I guess, fundamental techniques. Now of course we actually know a proving technique, we know induction. In fact, direct proofs are most of the techniques you probably have seen already in proving things. So if I, for example, showed a proof, I probably did it by direct proof. So in direct proof, this is just kind of just using definitions and following logic. Using definitions and I want to say logic, but really it's more like simplification. It could be like, well, let me just say other principles. Like for example, if you add a number to each side of an equation, that's considered the addition principle of equality. Basically applies some logical deduction somewhere. That would be a logical deduction. You can add a number to both sides and you get another result, basically. And you can continue with that. So just kind of use some definitions. For example, if you're given that a number is even, what does it mean for a number to be even? It means it's 2 times another integer. So then you write that out. And then you can apply some principles to apply some, like, I guess, manipulations of an equation or something like that. That's what I mean by principles. Okay. Proof by contradiction. Here what you do is you actually assume opposite of what you're trying to prove. So here let me say that when proving let's say if P then Q, we assume by way of contradiction, there's actually an acronym here, BWOC. You can use that if you want, just for shorthand. That stands for by way of contradiction. So assume by way of contradiction, Q is false. Which will lead to a contradiction. Let me have gotten cut off a little bit, but I wrote a contradiction there. Now the symbol for contradiction is actually 2 arrows crashing, like this. So 2 arrows crashing. Sometimes it looks like an asterisk, but it's really meant to be 2 arrows crashing. That's the contradiction symbol. Okay, so just to kind of understand what we're doing here, we are assuming the hypothesis to be true in an if-then statement that we're trying to prove. So let's imagine we're trying to prove some if-then statement. And we're assuming the hypothesis, we want to show the conclusion of that statement is true. So by way of contradiction, we'll assume the conclusion of that statement to be false. And if that leads to a contradiction, then that implies that what we were assuming to be false is actually true. Okay. Kind of strange, but it makes sense because remember, Q can either be true or false to proposition. So if we assume it to be false and we get something that's clearly false from our assumptions, like for example, I'm trying to think of an example right now. I can't think of one off the top of my head, but we'll actually see examples of all of these in a bit. But let me just say that, let's say whatever Q is, you assume it to be false, and then you apply your deductions and mathematical manipulations and all that of equations or whatever the case may be. Maybe it's an inequality, who knows. And let's say actually it's an inequality and you get something like 2 is less than 1. Clearly that's a false statement. That is a contradiction. So that means what you assumed to be true is actually false, assuming everything else you did in between was correct. Okay, now the next one here is a disproof by counterexample. The book actually wrote proof by counterexample, but I consider this more of a disproof. Very often this is used when you're trying to prove something to not be true. So if you have a statement, maybe by seeing a few examples, you can see an example stands out where, okay, this example contradicts that statement, so that means that statement's false. So that's a counterexample. An example I want to kind of bring up here are for mod primes. I'll just kind of explain real quick. A Fermat prime is a prime of the form 2 to the 2 to the n So it's a power tower, 2 to the n, and then plus 1. So Fermat, actually, he was a mathematician. Well, kind of. He was a lawyer, actually, in this time. But he did a lot of math recreationally. So he came about this expression and plugged in n to be 0, 1, 2, 3, and so on. And he found out that they're all actually prime. So he conjectured, meaning that he stated that it's probably true that this only produces primes. But that statement actually is false. And after he died, another mathematician actually found out that for a larger value of n that Fermat was unable to calculate, or maybe not calculate, but he was unable to verify if it was prime or not, unable to prove it was prime or not. This other mathematician actually proved that it was not prime. So that was a counterexample. I think it was like n equals maybe 6, something like that. You can look into it on your own if you want, but this is actually not true. So there is a counterexample to this. So these are not all prime. Okay. But still, if you have a prime of this form, it's still called a Fermat prime. Proof by cases are when you have a statement and it breaks down into, it's just what it suggests, right? What the name suggests. You break it down into different cases. You may have 2 cases, you may have 5 cases. Kind of depends. What comes to mind is even or odd. This is a pretty classic way to prove things about integers. An integer is either even or odd. So case 1, it's even. See what happens. Then maybe you can prove it in that case. So then case 2, it's odd. Then you have to prove that case. If both cases are proven, then that means it's true in either case. So basically you break your statement down into a few cases. If those are true for every case, then the statement is true no matter what. Fantastic. So now we'll see a few examples of each of these right now. Okay, so here in this example, we want to prove that for all integers a, b, and c, if b is a multiple of a and c is a multiple of b, then c is a multiple of a. So I want to prove this directly. Now remember, with direct proof, what I had suggested earlier is that we want to use definitions. Now, the big thing we'll be using definitions for is, well, I guess the big thing we'll be asking what is the definition of is the phrase multiple of. So what does it mean for b to be a multiple of a? So let me just say here, if b is a multiple of a, let me just write it like this, mult of a, then there exists some new integer, let's call it n, such that b is equal to a times n. So that I think makes a lot of sense, because if b is a multiple of a, like think of an example, like 6 is a multiple of 3. Why is 6 a multiple of 3? Because 6 is 3 times something. Namely, it's 3 times 2, but in this case, we don't care what that other number is. It's just some other integer. So in other words, there exists some other integer such that when multiplied to a will give you b, because b is a multiple of a. Okay, so we have that down. Similarly, if, write a comma there, if c is a multiple of b, so that's our second one here, c is a multiple of b, so we have this and. So this is part of our hypothesis, right? If this whole thing, then that. So we're trying to prove c is a multiple of a, assuming both of these are true because of the and statement, okay? Okay, so if c is a multiple of b, then there exists another integer, not the same one, but another one, let's call it k, such that, let's see, c is a multiple of b, so c is equal to b times something else, and then we're calling that something else k here. Great. So we've used definitions for what we were assuming to be true, and now let's get to what we want to prove. What we want to prove from this is the same as c is a multiple of a. So let's see what c is. C, we know, is equal to b times k. But b, we found to be equal to a times n if it is indeed a multiple of a. So I'll replace that b with an. So we have written c as a times something, a times nk. Notice nk is indeed an integer, so that means c is a multiple of a by the definition of being a multiple of something. Therefore, C is a multiple of A from this. And that's because this guy is an integer. N times K is an integer. That concludes our proof, so I'll write this tombstone. Now, if you want, you can write QED. These are just both kind of ways to remark that you finished the proof. QED is a Latin phrase, or it's an acronym for a Latin phrase that basically stands for what has been asked to be shown has been shown. You can look it up if you want. I believe it's like quod erat demonstratum, something like that. The tombstones are kind of just a symbol that stands for that, so it's the same thing. Some people use their own different markings too, but these are the standard ones. You don't even have to write anything if you don't want, but at least this tells me your proof is done. Okay. By the way, we will in the next video discuss a different definition, and it actually will lead to a new notation basically, that is essentially saying multiple of. So notice, B is a multiple of A means that A is a divisor of B, right? You can divide B by A and get an integer. So this is known as divides. So in fact, another way of writing this, the statement we're trying to prove is saying if A divides B and B divides C, then A divides C. And the divide symbol is, I'll just kind of show you, is this vertical line. So right here, this is A divides B. So that notation just would make this statement a little cleaner and also the proof a little shorter as well, just using that new notation. But we'll see that in the next video. That we're not going to be talking about now. It just comes to mind. Okay, so now on to the next example. Okay, so for our example of a proof by contradiction, I wanted to show this one. This is, of course, asking to prove that there are infinitely many prime numbers. Now, this is a very, very, very classic proof by contradiction, first shown by Euclid in maybe like 200 BC, way long ago, using contradiction. And it's kind of different because if you actually read the original reading of that book, which is called Elements by Euclid, it's known as the first math textbook, actually still kind of exists. I say kind of because it had to be translated from ancient Greek to modern languages and so on. But basically their concept of numbers was with lengths. So the way they describe things is it's really hard to it's hard to read, I guess, because we think of numbers very abstractly as quantities. They saw them as lengths. So to say a prime number, to discuss prime numbers, you would discuss a length that cannot be, I guess, factored or divided into smaller unit lengths, which is kind of hard to explain. Well, it's harder to phrase, I guess. So we know prime numbers to be the numbers 2, 3, 5, 7, not 9, but 11, then 13, not 15, then 17, then 19, and the list goes on. The next one is actually 23. Now you'll notice, first off, 2 is the only even prime number. And why these are prime numbers is because they cannot be factored further. So I said not 9 because 9 is 3 times 3. I also said not 15 because 15 is 3 times 5. Very often people will think, okay, prime numbers are just the odd numbers. It's not necessarily true. Though after 2, all primes are odd, it doesn't mean that all odd numbers are prime. Clearly 9 and 15 are odd numbers, but they're not prime. 35 is another example of a number that's odd but not prime because it can be broken down as 5 times 7. These numbers cannot be broken down further except as writing them as 1 times themselves, basically. Okay. So now that was just a recall on what prime numbers are. Now, the proof I'm going to use kind of will rely a little bit on what we discussed in the previous example with being a multiple of something else. Because if you are not a prime, then there exists a number smaller than you that is a multiple of you. So like 6 is not prime, 3 and 2 are factors of 6. They're numbers in which 6 is a multiple of. 6 is a multiple of 3, 6 is also a multiple of 2. So let's assume by way of contradiction, remember the BWOC, by way of contradiction, that there are finitely many primes. So there are not infinitely many primes, but that there are a finite number of primes. And in fact, we are going to write them in a list. P1, P2, P3, all the way up to P sub n. Okay? Now, these are n many primes. N may be a very large number, like a million, so there may be a million primes. Okay? In reality, we know there are infinitely many primes because that's what we're trying to prove. In fact, that's a true statement. There are infinitely many primes, as we'll see soon enough. But assuming contrary to that, then there are finitely many, so we can write them in a finite list like this. Now, of course, P1 is the first prime, which is 2. P2 is the second prime, which is 3, and so on. Okay, but we're just writing a finite list of prime numbers, and those are all of the primes. So this is a list of all primes, okay? So these are all of the finitely many primes. Now let's consider the following number. Let's consider the number, I'll call it capital N, and it's going to be a product of all of these, P1 times P2 times P3, all the way up to P sub n, but then plus 1. And now we'll consider the prime factorization of capital N. And there are two scenarios. Either n is prime, or it's not. Now, if it is prime, then we've actually discovered a new prime that is larger than these, because clearly multiplying a bunch of numbers and adding 1 gives you a larger number. So when n is prime, then there's a contradiction. So if n is prime, then this contradicts the assumption that there are finitely many primes. Let me just say it contradicts P sub n being the largest. Being the largest prime. It basically contradicts the fact that there would be a prime number that is the largest of the prime numbers, which is essentially what finitely many primes is equivalent to. If you say there are finitely many primes, then that means there is some prime that's bigger than all of the other primes. That makes sense. Okay, so there's a contradiction there. What about the other scenario? In this scenario, if it's not prime. So if n is not prime, then one of P1, P2, all the way up to Pn must divide n. Must be a factor of n. Because every number factors into prime numbers. And since, well, these are all of the prime numbers, this number must factor, if it's not prime, as one of those being one of the factors. But the problem with that is that all of these numbers are factors of this first term in the expression for n. So that would mean that if it is a factor of n, then it would also be a factor of 1. And that contradicts the fact that all of these are, well, doesn't contradict anything to do with the primes actually, but it's a contradiction because nothing divides 1, basically. The only divisors of 1 are just 1. So, so this also leads to a contradiction. It's a little harder to write that in words, so let me see if I can figure that out. Let me just say, this makes a factor of 1 that is greater than 1. I guess that's a way of saying that because all of these prime numbers are clearly bigger than 1, the smallest prime is 2. And if you have a prime that divides n, since the first term is the product of all of those, it would have to also actually divide 1 as well. And that's because when you divide both sides of this equation by one of these prime numbers, on this side, n over p will just be, it'll just be an integer because we're assuming p divides that evenly. And then if you split this fraction up as this all over p plus 1 over p, well, that's an integer, but then the 1 over p clearly is not because the denominator is larger than 1. So that would create a factor of 1 that's bigger than 1, and that is a contradiction. So right here, I'll write the contradiction symbol, like I could have written here, I guess. So therefore, what we assume to be false is actually true. Or I guess what we assume to be true is actually false. So we assumed there are finitely many primes. That led to contradictions all over the place. So now we can say, therefore, there are infinitely many primes now. So now we can say there are an infinite number of primes, all right? Infinitely many primes. I hope that makes it in the frame of the board. Awesome. And there is our tombstone. Now we can move on finally to the next example. Right, so this example is asking us to prove that if n squared is an even integer, then n is even. Now, I didn't say integer, but actually the phrase even or odd implies that the number we're talking about is an integer. It would make no sense to talk about an even or odd non-integer number. So like a fraction cannot be even or odd. Only an integer can be even or odd. So when you say a number is even, that implies that it isn't an integer, actually. Okay, that's the first thing. Second thing, I kind of missed one of the proving techniques. And the one I missed when I wrote down the list was contrapositive. So let me just kind of describe it here, and I'll actually write it like this. So contrapositive is an equivalent statement to an implication. So I'll write it here. This is an implication. This is equivalent to its contrapositive, which is negating these statements and reversing the implication. So if P then Q is equivalent to if not Q, then not P. These are actually equivalent, logically equivalent. And you can see that with a truth table if you want. A nice example I like to give people is living in a city within a state. So like, for example, if I live in, I'm trying to think of a city in, let's just say if I live in Los Angeles. Okay? If I live in Los Angeles, then I live in California. But if I don't live in California, then I for sure don't live in Los Angeles because Los Angeles is in California. And if you're not within that state, then you can't be in that city within that state. So I hope that makes sense. Okay, great. Now that's just an example of contrapositive, but again, you can see that these are equivalent with the truth table. So you can negate the thing separated by the if-then and reverse the order. Now actually, in reality, this is the reason why contradiction works. Because what you're basically saying is you're assuming the opposite of what you're trying to prove, and then you get to a contradiction. Now that contradiction may not be necessarily a contradiction of what you were assuming, like what your hypothesis is necessarily, like we saw in the previous example of infinitely many primes. One of the contradictions was something to do with divisors of 1, just being the only one. But that's kind of more general, I guess. You just get some contradiction. But here, you could actually do this by contradiction. I'll just kind of say it. So the hypothesis is n squared is even, okay? Assume by way of contradiction that n is not even. Then n would be odd. And then n squared is odd times odd. Odd times odd is odd. So that contradicts the fact that n squared is even. So in fact, what I'm going to do is I'm actually going to write the contrapositive of this, so we'll see that instead. But it's very similar to what I just phrased out loud with contradiction. So the contrapositive of this statement is if n is not even, so if n is odd, then n squared is not even. In other words, n squared is odd. And the reasoning I said this earlier, why this is true, is because odd times odd is odd. So let's prove this. So if n is odd, if you didn't know this, you can actually write any odd number as 2 times an integer plus 1. So let me just say for some k in the set of integers, you can also, if you wanted to, say there exists a k in the integer such that n is equal to 2k plus 1. I used that earlier, but here I'm using for some k in the set of integers. Same thing. Okay. Now, any odd number can be written as an even number plus 1 or an even number minus 1. So this is allowed. Okay. Okay. There exists a k that makes that work. Any odd number you think of, like 11, for example, is an even number plus 1. 11 is 10 plus 1, so k would be 5 in that case, because 2 times 5 is 10. Anyways, right, so we have a form for odd numbers. So now let's take a look at n squared. So now n squared then is 2k plus 1 quantity squared. And if you actually FOIL that out, you get 4k squared plus 4k plus 1. I'll allow you to check that on your own. And notice this is odd because it's an even number times 1, or an even number plus 1. So you can factor 2 from the first two. So you get 2 times the quantity, 2k squared plus 2k, and then plus 1. Since this guy here is an integer, we have written this n squared as 2 times an integer, in other words, an even number, plus 1. So right away we say that n squared is odd. And that completes the proof of the contrapositive. But since the contrapositive statement is always equivalent to the original statement, we've actually proven the original statement as well. Very good. So now we can move on to the next idea, and I think we'll see one of counterexample. Right, so here I have an example of disproving something. So let's disprove that for all integers n, this expression here, n squared minus n plus 41, is a prime number. Now, the way the book actually phrases this example is instead prove that there exists an integer such that this is not prime. So that's a nice way to think of it as a proof by example. But really we're creating a counterexample that disproves this statement. The problem with those statements prove that there exists a number that satisfies something. Usually that's, I guess, kind of existential. It is existential. Meaning you're proving something exists, right? And to prove something exists, you basically have to find that thing. In fact, that actually reminds me of something that I'll actually show below. Let me see. Prove that there exists an irrational raised to an irrational, which is rational. So I'm writing this down like kind of on the fly here, but and the way I worded this is kind of strange. I basically want to see what happens when you have an irrational raised to another irrational. Is it possible the result is rational? Now this is a little different because here we won't actually do this by example. We'll kind of create an example, sort of, but we'll actually show that this is possible. But that's actually a little different. It's quite cool to see that, so that's why I wanted to show that here. I hadn't planned on that though, so that's why I wrote it live like this. Well, let's see. So how do we disprove this? Well, first off, if you actually consider writing out some integers and plugging them into n squared minus n plus 41, when n is equal to 1, well, those cancel, you just get 41. When n is equal to 2, let's see, 2 squared is 4, minus 2 is 2, plus 41 is 43. Those are primes. When you plug in 3, well, let's see, you get 3 squared minus 3, that's 6, plus that is 47, that's also prime. And in fact, all of these will be prime up to 41 itself. How do I know 41 is going to work? Well, clearly when you plug in 41, you get 41 squared minus 41 plus 41. So the 41s cancel, and 41 squared is a number times another number. It factors as 41 times 41. So without doing any heavy calculations, I know right away that is not a prime number. So we have disproven this with this counterexample. So n equals 41 implies that n squared minus n plus 41 is not prime. By the way, I probably could have mentioned this earlier, but I, for whatever reason, chose not to. A number that is not prime is known as composite. So if you say an integer is composite, that just means that it can actually be factored. Okay, it's not prime. So now let's prove that there exists an irrational raised to an irrational which is rational. So what I'm going to do is I'm going to start off with a pretty commonly known irrational number, the square root of 2. There is actually a way to prove the square root of 2 is irrational using contradiction. You assume that the square root of 2 can be written as a fraction of two integers. That's what it means to be rational. And then you multiply both sides by b, you square both sides, you find out that a is even. A squared is even, but that means a is even, and we actually proved that in the previous screen. So I'll show that here. Multiply both sides by b, or actually, no, let's square both sides first. Square both sides, you get 2 is equal to a squared over b squared. Multiply both sides by b squared to cancel denominators. You get 2b squared is equal to a squared. That means a squared is even, but we proved previously if a square is even, then the original number is even as well. So that means a is even. Okay. Now, if a is even, then it's 2 times something, and you can divide by 2, and then you get b squared is even. Because it's 2 times something, but squaring that is 4 times something. Divided by 2, 4 divided by 2 is 2. You get b squared is even. Similar reasoning, if b squared is even, b is even. So actually what happens is that we reduce this to another fraction. You can divide by 2 basically. Now the quick way of proving this is to assume that this fraction is already completely reduced, and what we have done just now is contradicted that fact. If you don't like that, we've also basically kind of proven that you can infinitely often reduce this by 2, because you just reduce this to another fraction called r over s, and then apply the same exact logic, you can divide by 2 again. And that never happens. There's no irrational number that you can infinitely, that you can reduce infinitely often. So something to think about. But the square root of 2 is a pretty commonly known irrational number. So what I'm going to do is I'm going to take the square root of 2 to the square root of 2. Okay. So raising the square root of 2 to the square root of 2, that's an irrational to an irrational. There are 2 cases. Either it's rational or it's not. Okay. If it is rational, we're done. So this is either rational or irrational. If it's rational, we're done. Yay, complete proof. Tombstone. Perfect. So this is 2 cases. So it's kind of an example of proof by cases, really. But we're showing something exists, so that's why I'm bringing this up here. Okay. I still want to show you another example of cases, though. So even though this is kind of cases, I'll show you another example of cases after this, regardless. So if it's rational, we're done. If it's irrational, okay, then what we can do is we can raise radical 2 to that. So we don't actually know if this is irrational or not, but we just kind of started with this as an idea, thinking, okay, maybe this is irrational, but it turns out we're not really certain. Either it is or it isn't. That's fine. Let's just raise radical 2 to this. Radical 2 is clearly irrational, and in the case where radical 2 to the radical 2 is irrational, then we're raising this to this. So we kind of have this power tower of that. I'm sorry, I said it kind of backwards. I'm sorry. I want to raise this thing to the radical 2. There we go. That's what I wanted to do. Sorry. And now by exponent properties, we can see we multiply the powers. Radical 2 times radical 2 is just 2. And we have this. And radical 2 squared is back to 2, which is rational. So that means we found a scenario where we have an irrational number to an irrational number that is rational. Of course, this is only in the scenario if this base, radical 2 to the radical 2, is actually irrational, which we're not certain if that is the case or not. So it's one of those weird kind of scenarios where we've proven the existence of something, but we still don't know if this is rational or not. Kind of strange. Breaks down into 2 cases. One case we're done, other case start with something else, and we've at least shown that there exists a scenario where irrational to another irrational is rational. Interesting. Very, very interesting. Now let's take a look at the last example I wanted to discuss, which is an example of proof by cases. Okay, so here I asked to prove that this expression n cubed minus n is even for all natural, not natural numbers n, but for all integers n. So n, for all we know, could be negative actually. I'm going to prove this by cases. I find this one kind of boring because this is kind of what I said at the very beginning of this video. That sometimes you'll have a scenario where you consider if n is even or odd. That's what we're going to do here. So case 1, n is even. Case 2, n is odd. I actually have another way of showing this. I don't know if they're going to be the same or not. Just ideas I have. You don't know until you actually write it down. But let's write it down and see what happens. So there's 2 cases. So let me just say either n is even or odd. So we have the 2 cases. Case 1, n is even. So we can say there exists an integer k such that n is equal to 2k. Okay, then this is pretty simple. We get 2k cubed minus n, which is 2k. Well, 2k cubed is 8k cubed minus 2k. You can divide 2, pull that out. You get 2 times 4. K cubed minus k. This is an integer. Since we've shown that this expression n cubed minus n when n is even is 2 times an integer, then that means it is even. So this implies that n cubed minus n is even in this case. Perfect, that's done. Now what about case 2? N is odd. So in this case, kind of what we saw in the previous board, we can say that there exists some integer, let's call it j, such that we can write our integer n as 2 times that integer plus 1. If it's odd, it's an even number plus 1. Now we'll plug that in here. So we'll get our n cubed minus n expression. That's going to be 2 times j plus 1 squared. Oh, sorry, not squared, but cubed. Minus 2j plus 1. Trying to see if there's an easy way of showing this without actually expanding this out. If you want to use binomial theorem to expand this out, it's not too hard to do that. Maybe I'll do that. You can notice that they both kind of share this 2j plus 1 as a factor. You can pull that out maybe and see what happens there. But what I'm going to notice is that when you actually expand this out, the last term is going to be plus 1. If you distribute this negative, you get a negative 1. Those 1s cancel. Now, all of these other terms, when expanding this out, will be even because they're going to be multiplied by 2j to a power by binomial theorem. So we're going to have all even terms minus an even term. So those terms will all be even after the 1s cancel out. Then we can pull a 2 out and write it as 2 times an integer. I'll actually show that. So expanding this out, I get that to the 3rd power, which is 8j cubed, plus the second binomial coefficient in this expansion is 3. 3 times 2j to the 2nd, that's 3 times 4j, which is 12j squared, plus, again, 3 is the next binomial coefficient, if you remember the 1, 3, 3, 1 for the 3rd layer of Pascal's triangle. And then we have 2j to the 1 now, so it's to the 3rd, to the 2, to the 1. And then the power of 1s just increase, so it doesn't do anything here to these terms. So you have 2j to the 1 times that, that's going to be 6j. And then finally plus 1 because it's 1 to the 3rd. So again, if you don't like that, you can expand it out, write this as itself multiplied by itself 3 times, expand it out, you'll get that as well. Minus, so let's distribute that negative, we'll get negative 2j minus 1. As promised, those 1s indeed cancel out. Very good. So after seeing those 1s cancel, we notice that we can actually, well, I guess we can combine those to 4j, so that's fine. Let me do that here. So we have 8j cubed plus 12j squared plus 4j. It's all pretty easy to follow, I guess. It's just a little bit number crunchy in the expansion of this, but that's okay. Pull the 2 out, we have 2 times the quantity 4j cubed plus 6j squared plus 2j. This expression is clearly an integer because it's a combination of integers that does not include division. By multiplying and adding, even subtracting integers gives you an integer still. So this is 2 times an integer, so that means in this scenario, n cubed minus n is even. We have shown both cases provide the correct result, that this is indeed even. So altogether, after proving case 1 and case 2, now we can finally say that this is indeed even for all integers n. We proved it for all odd integers and then separately for all even integers. Since every integer is either even or odd, now we've proven it then for all integers. Fantastic. Now I did say I have another way of seeing this. That is not a case scenario. Let me explain. In red. This expression has n in common, so you can factor n out, which is kind of what I suggested here. To simplify this, you can factor that out. Also, n squared minus 1 is a difference of squares. It's n minus 1 times n plus 1. Now, this to me is actually very interesting because we have consecutive integers here. In fact, the real way to write this is n minus 1 before n, so we write them consecutively. So I'm going to swap n minus 1 and n in this multiplication just to kind of show that these are consecutive. For example, let's say n is 5. If n is 5, then that's 4 times 5 times 6. Right? 5 minus 1 is 4, and it would be 5, and 5 plus 1 is 6. So you have 3 consecutive numbers multiplied. Now, it kind of breaks down into cases because either n is even or odd. If n is even, we're done because we have a product of even numbers. If n is odd, then the other numbers cited are even. And you have an even number in its multiplication, so that means it's even because it's a multiple of 2. So in fact, multiplying any 2 consecutive numbers will always be even, as long as those numbers are integers, of course. Will always be even because one is even and the other one's odd, but multiplying an even number by any number, even or odd, makes it even still. So that's a different scenario, kind of casey, I guess. You can probably get away with proving it by cases, but I think it's a little more straightforward and a little more simple. And in fact, if you remember triangular numbers are all of the form n times n plus 1 all over 2 without the n minus 1 part. And that explains why those triangular numbers are all integers. Any number, any integer of the form n times n plus 1 over 2 is an integer. That would imply that n times n plus 1 is even because you can divide it by 2. Clearly you can. The reason why that works is because any 2 consecutive integers multiplied will be always even because one of those numbers is even. Great. So that concludes our discussion on proofs. We saw a lot here. I really hope you enjoyed it. Try to give as much variety as I could in proofs. And I had a lot of fun actually writing these out. So I hope you had a lot of fun watching and trying alongside me. So that's great. So thank you all for watching, and I'll see you in the next video where we'll be discussing an intro to number 3. It's going to be a lot of fun. Hope you enjoyed this. Thanks for watching, and I'll see you then.